Let's talk about blood pressure and cardiac output. Doctors often use those two terms, and we hear the numbers, but we're not sure whether they are related, somehow related, and what's the link between those two. So let's break it down into simple engineering terms. So I'm gonna do this explanation for the left side, the systemic side of the cardiovascular system. However, the same logic applies to the right side, the pulmonary side of the cardiovascular system. The numbers will be different, but it's the same structure, same explanation. However, today I'm going to talk about systemic vascular resistance and cardiac output on the left side of human circulation. To simplify this discussion, let's divide the system into two components: the pump, our heart, and the resistance, which is the vasculature, the arteries that are hooked up into the left ventricle. So, as blood is being ejected from the pump, it goes into the pipe or a network of pipes, which we called systemic vascular resistance, and then it creates flow and pressure within the system. So, let's see how it works. Uh, I'll draft for you a simple graph. And on this graph, you will see how those two components of the system, the pump and the resistance, work together. So here you see on this axis, you see flow or cardiac output. That's the blood flow that comes out of the left ventricle. On this axis here, you see blood pressure. That's the arterial blood pressure. Again, it's the mean number. It's not the pulsatile pressure. We are talking about average mean numbers for cardiac output and pressure. You see two lines. One is a straight blue line that represents systemic vascular resistance behavior. It's a typical resistive behavior. What does it mean? It means that as we increase flow, we increase the pressure drop across the resistor. That forms this straight line that goes up. Again, any resistor behaves the same way. It's linear. In reality, might be slightly nonlinear, but linearity is good for our model here. You also see the red line. The red line represents the pump behavior. So what's the difference? Well, pump is active. Pump provides energy. However, all pumps have the same problem, if you will. As they increase flow, the pressure will drop. The pump cannot sustain the same pressure as it increases output flow wise. Now, those two lines cross. You see the intersection between the systemic vascular resistance and the cardiac characteristic, the flow pressure cardiac characteristic. This point represents the status of our cardiovascular system, in this particular case on the left side. So the combination of cardiac output and blood pressure, they have to be on those two lines together. So the intersection represents the cardiac output and blood pressure pair that is actually present inside our cardiovascular system. Cannot be in any other place. Now, what happens if the systemic vascular resistance changes? Well, you see in this animation that as we change the systemic vascular resistance, the pressure and flow combination change because the intersection slides on the cardiac curve, right? So as the systemic vascular resistance goes up, the point goes to higher pressure and slightly lower cardiac outputs. This is why we should have a balanced systemic vascular resistance, so it gives us enough perfusion and enough pressure for our physiological needs. So this is how it works. Next time, we'll discuss how changing the cardiac characteristic changes this combination of cardiac output and arterial blood pressure.